So in the previous example, we found the electric field outside the shell, or outside the uniformly charged sphere which had a radius of r. Now what we want to do is find the electric field inside the shell. Okay, so yet again, let's just draw our sphere, which is here. It's positively charged, so we've got lots of positive charges in here. And this uniformly charged sphere has a radius of r. And the total charge is Q. Okay, so what we do now is previously we drew our Gaussian surface around the outside. Now what we do is we draw our Gaussian surface, which is going to have a radius smaller than the radius of our sphere. So here's a Gaussian surface in here, and its radius is going to be given by r. So again, the shell is concentric with the outside, and now what we're going to do is look at what the total charge is contained within our Gaussian surface. So clearly the total charge which is within our Gaussian surface is only going to be a portion of the total charge Q. So now what we're going to do is define our charge density per unit volume. So we're going to have rho is going to be equal to dq dV. Okay, so it's that part of the charge which is contained in some specific volume. Now, the charge which is going to be enclosed in our Gaussian surface then, which is going to be Q enclosed, will be equal to the ratio of the charge enclosed by the Gaussian surface and the charge enclosed by the total sphere. So it's a ratio of the two volumes. So what we have here is 4 over 3 pi or cubed by the density rho. And on the bottom we consider the volume of the larger sphere. And all of this is times the total charge on the outside. Okay, so on the top line we've got the charge density times the volume of our Gaussian sphere, and on the bottom we've got the total charge density of the overall sphere. Okay, so it's the charge density multiplied by the volume. So what we can now write is we see that a number of things are going to cancel. So we've got the 4 over 3 cancels, pi's are going to cancel, and the rho's going to cancel. So now what we're left with, the total charge enclosed by a Gaussian surface is going to be simply equal to r cubed over big R cubed times Q. Okay, and again, Q is the total charge over that uniformly charged sphere. So now that we know this, we can write down Gauss's law. So for Gauss's law, we're going to have our surface integral of E dot dA will be equal to little r cubed over big R cubed by epsilon naught times Q. So remember again, because we got with symmetry and we have a sphere, the electric field is going to be pointing radially outwards. Our surface area element, when we integrate it over the surface, it's going to be given by 4 pi r squared. And because the electric field is going to be constant and uniform over the surface, it can be brought outside the integral. Okay, so we looked at that in the previous problem, but now what we have here is the magnitude of the electric field times 4 pi r squared going to be equal to r cubed over big R cubed epsilon naught by q. So our electric field is going to be given by 1 over 4 pi epsilon naught little r over r cubed times q, and it's in the r hat direction. Okay, so here's our final answer. We can see that if we were at the surface of our shell, the r's are going to cancel, and it's going to be as if all of the charge is just concentrated at the center. We're going to have that 1 over r squared dependence. Okay, so let's plot this. There's r, so it's a distance away from the center. Here we're going to have the magnitude of our electric field, and what I'm going to put in here is a line where little r is equal to big R. Okay, so big R is the radius of our charged sphere. And what we're going to find is that inside the sphere, the magnitude of the electric field is going to increase linearly with R until it hits R is equal to big R, and then it's just going to decrease as 1 over R squared.